All right, let's talk about electric charge. Right, every week in this class I feel like it's and now for something completely different. So here's what we know about charge. There's two kinds of it. So I'm going to note this with blues and reds. For historical reasons, we call these positive and negative charge. And what we know is that like charges tend to repel each other. So these two red charges are going to push each other away. And so are these two blue charges here. But there's an attractive force between unlike charges. Right, so this knowledge is old in humanity, centuries old. Before we learned to really control it, we still knew that there was something there. And now we know that there are, in most cases, two particles that carry charge. So the negative charge is carried by electrons, and they're really tiny. The mass of an electron is it's approximately 9.1 times 10 to the minus 31 kilograms. Positive charges are carried by protons. They're also tiny, but they're 1,000 times bigger than electrons. And if you've had chemistry, which I assume all of you had, you know that for the most part, electrons and protons occur in equal numbers in objects. There are ions out there, but ions really like to bond with things that give them a neutral overall charge. So at the atomic level, we're generally neutral, right? And at larger scales, we're almost always neutral, right? Because electrons and protons are found in equal numbers in, say, this nucleus of helium. There's two protons, two neutrons, and then there's two electrons in orbitals about that helium atom. However, just because we're neutral overall doesn't mean that we can't get some electrons to leave their posts. Right? So the easiest way to do this, to demonstrate this, is to just maybe take a balloon, rub it on your head, your hair will stand up, and then the balloon will stick to the wall. So what you've done there is you've actually rubbed some electrons off of your hair onto the balloon. And so now there's net charge on both of those objects, right? Your hair has a net positive charge and the balloon has a net negative charge temporarily, right? They will go about equalizing themselves as quick as they can, but for the moment they will have some net charge. So let's talk about that for a moment. I'm bad at drawing things, so here's a person who has rubbed a balloon on their head. And there's the balloon that they rubbed on their head stuck to the wall. as we just said, the person's head now has a slight positive charge, and this balloon has a net small negative charge. No protons got moved around. Protons are really happy just hanging out in the nuclei of atoms. They're really stable. So unless you chip off a block of bulk material, the protons are not going anywhere. Electrons are more happy to move around, being 1,000 times lighter than protons. So there is a positive charge on the head of the, person who has been playing with balloons, but that's not because protons have been transferred to their head. It's because there's a lack of electrons on the person's head. So sometimes we refer to these as electron holes or electron deficits, but that's what's going to cause a positive charge, is a deficit of electrons. And what's going to cause a negative charge is a surplus of electrons. All right, this should be review for everyone from chemistry so far. Something that we are going to expand upon, though, is the electrons electrons are not equally mobile in all materials. There are materials that we refer to as insulators. And in insulators, electrons are pretty stable. So they like where they're at, and they're not going to move around. Moreover, if there is, for some reason, electrons being tossed at this insulator, they are mostly going to bounce off rather than penetrate. The other kind of material that we are going to concern ourselves with is a conductor. In a conductor, electrons are relatively free to move around, so an electron that started off connected to one atom can maybe switch places and associate itself with a different atom. It's also possible to knock electrons out of a conductor, and it's also possible for electrons to penetrate into a conductor. So when we say conductors, usually we mean metals. So metals are usually good at conducting electrons, and that's because of the kind of bonds that usually happen in a metal. So does everyone remember what the 3 kinds of bonds are from chemistry?
Covalent, ionic, and hydrogen.
Hydrogen bonding is an intramolecular force, not an actual bond.
Metallic?
Metallic bonds, that's right. Covalent, ionic, metallic. So in ionic bonds, we have here I'm gonna sketch really quickly an ionic solid. Lots of ionic materials have really simple crystal structures. Like table salt has just a really simple cubic shape. There is an atom on each corner of the cube. And that is it. In these atoms, they will alternate being positive or negative. So all the sodium, all of the sodium atoms are going to be positive. So say like there's a sodium there, sodium there, sodium there, sodium there. And all of the chlorine atoms are going to be fully negative. Okay. When you have this this sort of bonding in a solid, not a lot of charge transfer can happen. If you dissolve it in water, of course, you have an electrolyte, and then you have positively charged and negatively charged, nuclei that you can just push around. But in physics, most of the time we're going to be concerned with the way that solids behave. Where in chemistry, you're usually concerned with the way that liquids behave. In a covalent structure, you might still have a simple structure. So my research is actually on aluminum. And aluminum also has a cubic structure. Here I'm just going to draw one face of it. The difference being aluminum also has an atom in each face of the cube. And so you get actually two kinds of bonding. You get these bonds along the length of the square, and you get these bonds at the diagonal. And these diagonal bonds are shorter. So in a covalent bond, all of the atoms themselves, they're like a little bit positive. All of them. And the electrons hang out in between. So there's negative charge concentrated between these atoms. And I know I just said that aluminum has covalent bonds, and it does. So aluminum is a metal, but it also has some covalent bonding. It just so happens to be the one that I'm most familiar with. And the last kind is metallic bonding. Here I'm going to take copper as the example. It has exactly the same structure as aluminum, where it's got an atom on each corner of a box and an atom in the face, or in the center of each face. And in copper, in metallic bonding, like copper, again, all of the atom locations are positive. But instead of the electrons being, hanging out between pairs of atoms, they're just kind of wherever. So in a metal, the electrons can be found wherever. And so if there's no particular preference for any place for the electrons to be, they might as well move within the material. That's what makes metals good conductors. So electrons are free to occupy any position inside a bulk piece of metal that they desire. All right. Let's be a little bit more quantitative instead of qualitative about this. So think back to Gen Physics 1. What's the most important formula you learned in Gen Physics 1?
I'm sorry, what was the question?
What is the most important formula that you learned in 151 in the first semester of physics? Yeah, Cindy, Shelby, right. F equals ma. Is the um, one of the bedrocks of physics as a way of analyzing the world is we think of things in terms of forces and movement. And so if we're going to really start studying how charge behaves, the place we have to start is considering what kind of forces charges exert on here we've gotten up to section 3 of chapter 18. Oh. Just a moment, friends. Why is... Oh, never mind. So the force between two charges, we'll write this as Coulomb's force. Part of this we can reason out. So the stronger a charge we're dealing with, the stronger the force we expect between two charges. So we're going to go ahead and put the charges in the numerator. So the bigger they are, the bigger we expect the force to be. And if you think back to gravity, right? So the force of gravity, right? Some constant product of masses divided by square of the distance, right? So physicists, prefer to think in terms of what they're already familiar with. So it becomes natural to try and pattern our force law for charges based on the force law we already know for masses. And that actually turns out to work really well. So we know that the further apart charges are, the less effect they have on one another. And so we might expect that there be some distance in the denominator. And just like with the gravitational force law, that's going to end up being squared. And we'll slap on a constant to make all the units work and to scale it however we need. But then there's one missing piece with Coulomb's law compared to Newton's law of gravitation. We will note that both of these force laws act along the line connecting the two masses. So this r hat means a unit vector in the r direction. So for example, if we have these two particles, whether they be charged or massive, the r direction it just points from one particle to the other. Right, and then and similarly, we might say that the r direction for the second particle goes back toward the first. So in gravitation, masses can only be positive, and the force between two masses can only be attractive. But in the electrical force, the charges can be either positive or negative, and they should only be attractive if we have opposite charges, and they should be repulsive if they have the same charge. And so we add a negative sign. So if both of these, if both Q1 and Q2 are positive, or if they're both negative, then the main body of Coulomb's law here will be positive, but we need it to be repulsive, a repulsive force, so we add it, so the negative sign out in front will take care of it. Now, Coulomb's law is going to govern the next, 2 weeks of study, just like Newton's law dominated your study of Gen Phys 1. Now, just like with the gravitational law, though, we very seldom broke out this full gravitational law, right? Like most of the time in...
You get eating.
I'm sorry?
Oh, I'm sorry. I didn't realize my mic was on.
So in Gen Phys 1, we very seldom broke out the full gravitational law. Most of the time, we said something like, well, the force due to gravity is just m little g if we're near the surface of the Earth. And if, so basically we took all of these pieces here, and we said, well, all of this put together, that's g, where capital G is some universal constant, m1 is the mass of the Earth, r is the radius of the Earth, and if we plug all that together, we get g, which is about 9.81. Another way to think about that is that this g, m1, and r describe what could be called the gravitational field of Earth. And if you place a mass into the gravitational field that Earth creates, then you're going to that mass is going to experience a force. We're going to use Nicholas, I haven't said what k is equal to yet, so don't worry about it. We're going to use the same strategy for Coulomb's law here, if we can. We're going to say that this stuff here, this k, q1, and r squared, all of this together, we call that the electric field produced by charge 1. And if we place a charge into an electric field, it's going to experience a force, the same way that if we put a mass into a gravitational field, it'll experience a force. I actually meant to include the negative sign in there. All right, and then so Coulomb's full law is this k q1 q2 over r squared, but we'll frequently be saying, Coulomb's law is just electric field times charge, EQ. And physicists love these little one thing equals the product of two things laws. So that's really aesthetically satisfying, as well as simpler to think about too. Let's talk about electric fields for a minute, and then we're going to do some problems. So here's my plan for the rest of the first half of class. We're going to talk about how electric fields behave, and then we are going to do some problems involving Coulomb's law and electric fields, and then we're going to take a little break so that we can all stretch our legs. All right.
What was EQ again?
I'm sorry?
EQ? What was EQ again?
Yeah, so the Q, these are...
EQ.
E? Oh, EQ. This is... Here,
Yeah.
let me... So this is the... Right? That's this
Electric
E.
field.
Yeah, electric field. And Q is the charge we're interested in. Multiply them together, and you get the force.
Okay, picture.
Yeah. Capital G for the gravitational charge is something that you can just look up. K is really easy to remember. actually. The value for K, as long as you're using SI units, and the units we should be using here are coulombs and meters and newtons. The value of K is approximately 9 times 10 to the 9.
Are there any units associated with K, or is that one that has no units at all
Yeah.
associated with it?
There are units associated with it, and the units are such that it takes this Coulomb squared over meter squared, and makes it and converts it to newtons. Right, so it's meter squared newton per Coulomb squared. Right. But the units on that don't really have a meaning, except that we want to make the units work out so that we have forces in newtons on one side, and on the other side we've got charges and distances.
Thank you.
Right. So when we're imagining electric fields, it's what we usually do is draw what we call field lines. Oh, I misspelled fields here. So if we have a negative charge, take a look at our minus kq over r squared. If q1 is negative, and we have a negative sign as well, so that's going to be, those are going to cancel out and give us a positive. And so the field lines point toward negative charges. Meanwhile, if you've got positive charges, the field lines will point away in every direction. Right, and there's nothing special about the particular arrows that I've drawn here. There's an infinity of them, right? There's a good section in the book on how to deal with field lines. That's section 5, and the idea is that the more of these arrows that you draw, that's like a qualitative indication of how strong the electric field is, and then the direction, of course, is important. But my art skills aren't great. I don't expect the rest of you to have great art skills either. So we're going to focus more on the calculation of strength rather than we are drawing super accurate pictures.
Question.
When you're looking at these, would you say that the importance is to look at how many arrows there is, or like the length of the arrow to determine the strength? And that's one thing that confused me when I was reading.
Yeah, so that's a good question. So in Gen Phys 1, the length of the arrow we drew was really important for determining the strength of the vector. Here, it's like how closely packed the lines are. That's the expectation, and the reason for this is that electric field lines can actually be bent, not straight, and that. So you actually let me segue into the next thing I was going to mention, which is that you get very interesting things if you have multiple charges. So we know electric field lines prefer to go toward negative charges and away from positive charges. So that's an easy line. Fallon asks, is there any relation between this and the field around the Earth that protects us from solar radiation? Yeah, and we'll get to that in a couple of chapters. It's actually the magnetic field of the Earth that does more of that protection, but we'll get to that in a couple of chapters, don't worry. So the first electric field line is just from the positive to the negative. Easy. But we know that electric field actually goes out in all directions from a charge. So what happens to the electric field that comes down south of this positive charge? Well, it also wants to point toward the negative charge. So we get this curved line. We get something similar for the top. In fact, it's extreme enough that we'll get some electric field pointing straight away if it's directly on this axis, but if it's even a little bit off, we'll see it curving around and joining up with the negative particle on the other side. So this is why we don't necessarily pay attention to the length of the vector lines, because we're actually drawing a path that the electric field takes. Like, what direction does the electric field point at every direction in space? Right? You might see some diagrams that have some extra arrowheads drawn on here just to help you remember which direction they're going. Again, there's a really good section about this in the book. We won't be focusing on it too heavily. What's important to know is that electric field lines go from positive to negative, and the reason that field lines are important is because if you put a charge down in the electric field, the force that the charge experiences will be in the same direction as the field for positive charges. So positive, if you put down a positive charge, say right here, the force on this positive charge is going to be in the same direction as the field. Now, if you plop down a negative charge, right, the negative sign on the negative charge is going to reverse the direction of the force. So yes, I know that these negative signs can be confusing. It's a lot. Like just letting there be positive and negative charges makes this a lot more complicated than gravitation already. And all I can say is that as you do some problems, this will become more like second nature. So, two things we want to keep in mind is there is a direction for electric field. It's from positive to negative. And two, that positive charges move with the field. Negative charges move against the field. Okay. Are there any questions or comments that we can deal with now before we jump into some problems?
So just to make sure with that second point, you're just saying that positive always moves to negative. Negative doesn't necessarily move to positive.
No, negative does move to positive.
Oh, okay.
Right? So like this negative charge, this red circle down here, is moving along the field line toward the positive charge, right? And
Okay.
the positive charge in blue up top is moving along the field line toward the negative charge.
Okay, I see.
Okay. So let's do some problems from chapter 18, and then we will take ourselves a break. So I want to remind everybody that there's too much in these chapters for me to cover every single good problem or every single detail. We just don't have that kind of time. Like, I wish we did. We don't. So you have to read the chapters and do more problems than I do in class. Alright, let's do a plug and chug problem here. Let's say that we position a charge which has a charge of positive 2 microcoulombs, so that Greek letter mu means micro, so it's 10 to the minus 6 coulombs. Is placed halfway between a charge of positive 6 microcoulombs and another of positive 4 microcoulombs, separated by 10 centimeters. What is the magnitude of the force on our 2 microcoulomb charge, and what direction does the force point? All right. So let's go through this this problem a piece at a time. This is a really good opportunity to practice the problem-solving method that we should have perfected in Gen Phys 1. We'll start by drawing a picture. We will specify our coordinate system. If we have a two-dimensional problem with some vectors, we'll break down the vectors. We will identify what physics governs the situation we're looking at, and then lastly we'll do the math to get whatever variable of interest we're looking for. Alright, so we're dealing with all positive charges here. We've got a 6 microcoulomb charge. We've got a 2 microcoulomb charge. And we've got a 4 microcoulomb charge. The problem says that the middle one is halfway in between the outer two, and that there's 10 centimeters between the outer two. So that means there's 5 centimeters between the middle and either of the outers. We're going to do this problem two ways. We're going to use Coulomb's law directly, and then we're also going to calculate the electric field and use the field method. We're going to say that to the right is the positive direction. No particular reason. And the physics that we're going to bring to bear on this problem is, first we're going to start with Coulomb's law. So the force experienced, so the force between two charges is minus k q1 q2 over r squared. I think your book omits both the negative sign and the r hat bit, and says to calculate the magnitude of the force first, and then use your knowledge about opposites attracting and likes repelling to specify the direction after the fact. That's perfectly okay. So let's actually use that strategy here. So there are the middle charge, which we will say is particle 2. This is particle 1. This is particle 3. So the net force on 2, it's going to have two pieces. It's going to have a force due to charge 1, so the force of 1 on 2. And it's going to have the force due to 3, so the force of 3 on 2. Now for the force of 1 on 2, particles 1 and 2 are both positive, so they should repel each other. So what direction is the force from particle 1 on particle 2 pointed? Is it pointed to the right or the left?
So, oh yeah, left.
We have left, we have right. That's all possible answers. So if there is nothing else in the universe, just charge 1 and charge 2, and they are repelled, that means charge 2 wants to get away from charge 1. So charge 2 is going to be moving to the right. So the force from particle 1 to particle 2 will be to the right. Of course, Newton's third law tells us that the force from particle 2 to particle 1 will be the left. So particle 1 will feel a force to the left. Particle 2 will feel a force to the right. The right, we've said, is our positive direction. So yeah, we'll leave that as positive. So we have K, Q1, Q2 over the distance between 1 and 2 squared. Now what about 2 and 3? 2 and 3 are also both positive, so they will also be repelled. So in what direction is particle 3 going to shove at particle 2? Yeah, this time I'm seeing 100% lefts. That is correct. So particle 2 is going to want to move to the left to get away from particle 3. We've said that left is the negative direction, so we'll plop a negative sign in here. We can be taught, says Elizabeth. So we'll plop down the negative sign to indicate that it's going to the left. Wow, I used 1 and 2. I meant 2 and 3. All right. And now we've got everything, so we can plug in. You do need to be a little careful with all these scientific notation exponents flying around. First person to get me the number for this calculation gets 6 internet points.
I'm sorry, what?
If you, the first person to finish this calculation here gets 6 totally worthless internet points.
Okay, I don't understand the over 5 times 10 to the negative 2. Why?
Because centimeters, right?
Yeah, but why is it 5? Aren't we going from 6 to 2?
6 to 2, that's the amount of charge, but the distance between them is 5 centimeters.
Gotcha.
Yeah.
Okay, there you are. Yep, got it.
Anthony, I think the correct question is, what's the conversion rate of internet points to Shroot bucks? Right? Shroot bucks is where it's at. Oh, and it's William Peters by a nose. You get the totally worthless internet points for the day. So total, right? We do all the calculation over here. We're going to get something like 14 newtons. And because we got a positive number here, that tells us that the net force is actually going to be to the right, which we called the positive direction. And that makes sense, right? So the 2 microcoulomb charge is repelled by both of the positive charges around it, but the charge on the left is bigger, so it's repelled more by that charge.
I'm sorry. Could you just go over the directions again? I got all the math necessarily, but the directions were kind of what confused me, because I understand that because 1 and 2 are both positive, they push against each other, and then 2 and 3 are both positive and they push against each other, going in opposite directions.
Right.
So when you were asking what effect 3 has on 2, I was thinking that 3 goes to the right because it's pushing against that, and so it's going the opposite way. And so when you said it was left, I was kind of confused.
Yeah, so particle 3 is going to want to move to the right. But if particle 2 moves to the right, that means it's moving toward particle 3. That's the opposite of what it wants. It wants to get as far from 3 as possible. Does that make sense?
I see. So we're looking at the effect on 2 at all times. We're not necessarily looking at anything else.
Correct.
Okay.
Yeah. So for this problem, our system is particle 2 alone, and particle 1 and 3 are considered external forces.
Okay, that makes a lot more sense then.
Will we see a problem like this on next week's quiz? Probably. So let's also do this problem. Oh, 2 will move in the direction that has the most force behind it. That's right. So if you've got if you think in Gen Phys 1's terms, if you've got two people trying to push a box, one's trying to push it to the left, the other one's trying to push it to the right, the box will move in the direction of whoever is strongest. And in this case, we've got two particles, particle 1 and particle 3, both trying to shove particle 2 in opposite directions. Whichever one has the most charge wins.
When that happens, 3, since it's smaller than 1, it will actually get pushed further to the right. Since two is being pushed to the right and 1 has the higher charge, 3 will be pushed farther.
Sure. But particle 3 is outside of our concern for now. But yeah, particle 3 will get pushed to the right pretty fast. Anthony Lopez brings up a good point, only because they are equidistant. That is true. If particle 2 was closer to particle 3 might actually exert more force even though it's got less charge.
So for this part, for part A, the magnitude would be that 14 newtons, and then for part B, the direction would be in the positive direction to the right in this case?
Correct.
Okay.
So let's solve this problem with electric fields too. So what we're gonna want is the total electric field is going to be the electric field due to 1 plus the electric field due to 3. And remember, the electric field is going to be the kq over r squared. So the electric field due to 1, at a distance of 5 centimeters to the right, is going to be 9 times 10 to the 9 times 6 times 10 to the minus 6, all divided by 5 times 10 to the minus 2 squared. Hanson, we're going to get to that in the next problem. So someone check my arithmetic, but what I get here is we have 21.6 times 10 to the 6. And the units here will be newtons per coulomb. Right? That'll be the strength of our electric field. Now, we want to also calculate the strength of the electric field due to particle 3 at a distance of 5 centimeters to the left. So because electric fields go away from positive charges, we know that the direction of the electric field to the left of particle 3 is going to be to the left. that is the negative direction. So we know there's going to be a negative sign out front. And then we're going to have a lot of the same stuff here. 9 times 10 to the 9. 4 times 10 to the minus 6. And 5 times 10 to the negative 2 squared. Here we get minus 14.4 times 10 to the 6, not negative 6, positive 6 newtons per Coulomb. So then the total electric field is going to be these two things added together. So there's the net electric field due to charges 1 and 3 at the location of charge 2. I'm running out of room a little bit. Going to go down to the bottom left corner. I apologize. I know it's a little sloppy, but I wrote too big. So if we want the net force on particle 2, well, we just need to multiply the electric field times the charge. Which is, 14.4. So we use two different methods to get the same answer. It's comforting that both methods gave us the same answer, which means both methods are okay. This is somewhat analogous to how in GenPhys 1 you could use kinematics or energetics to get some of the same answers. But for more complicated questions, it was almost always better to use energetics instead of kinematics. And that's going to be true here too, that both of these methods are going to give you the same answer, but for more complicated problems, it'll usually be easier to deal with electric fields instead of directly with Coulomb's law. So the values of E1 and E3 are the electric field due to charge 1 or charge 3.
And the point the 0.05s that are within parentheses, those are just symbolizing the distance that's occurring between each of the 2 points. It's just like a symbol. It's not necessarily like a something to be multiplied.
Right. It's like the argument of the electric field. So it's like saying f of x in math.
Okay. I see.
So the electric field, will the electric field from a point charge will fall off with distance. And so when we want to calculate the electric field, we have to calculate it at a specific distance. All right. Any other comments, questions, concerns, panic attacks?
Definite panic attacks. But
I appreciate your honesty, sir.
No, that was during the quiz.
Why is the second method recommended? Just because it'll end up being easier when we have more complicated problems. Like, this is basically the simplest, arrangement of charges that we could imagine. Just 3 charges, all the same sign, all in a line. So it doesn't really matter which method we use. But the more complex a problem gets, the easier it'll be to talk about it in terms of fields. So yeah, we start with forces because forces are something you all are familiar with from Gen Phys 1. But really, we want to talk about things in terms of fields. So that's the kind of syntax that we use for electricity and magnetism. Alright, so by my clock, it is 12:55 p.m. Let's take 10 and come back here. Well, actually, we're a little behind. Let's take 5. Come back here at 1 o'clock, and we will start chapter 19.